All right. So at the top, it's the one-to-one property, which we kind of have already looked at with our table of powers. So if the base is the same, right, 3 and 3, all we need to do is make the exponents the same. On number 2 and number 4, we're going to make the base the same before we do the exponents, because this is a half, this is 4, so we can make them both into like a base of 2. So in number 1, if the bases are both 3, you can just go ahead and set your two exponents equal to each other. So if you set them equal to each other, you're just solving a linear equation. 6x plus 1 equals 4x minus 1. So you're still solving an exponential equation, but it's really just a linear equation that you're solving. Combine like terms, right? So subtract your 4x to the other side. So you get 2x plus 1 equals negative 1. Subtract 1 to the other side, and then divide by 2, right? We're just trying to get x by itself using algebra. So subtract 1, so you'd have 2x equals negative 2. Didn't leave myself enough room. So x is negative 1, right? So it's not anything new with the exponents itself. It's just setting them equal, recognizing that you've got the same base, so the exponents have to be equal. So on number 2, we had done one like this on the quiz where you just had to come up with the correct power, but I only put x on one side on the quiz. So now you've got x's in both exponents, so it makes it a little bit harder, and we don't want to just guess and check. So what you're going to do is you're going to force both of the bases to be the same. So these both come from the power of 2 family. So instead of writing 4 on this side, I can represent 4 as 2 squared to the x power. So 4 and 2 squared are equivalent. So you always want to take the bigger number and bring it down to the other base. You don't want to make this 4, because if you take 2 and square 4, you've changed the value. This is just 2. 2 squared, this is just 4. So it should be equivalent at the end. Then you're going to use your exponent property. What's the rule when you distribute exponents? What do you do to them? Do we add or multiply when we distribute exponents? No one knows? Yeah, just multiply, right? So this is really 2 to the 2x power. And over here, I still have 2 to the x plus 7 power. So now I'm at the same step that I was in number 1. The bases are the same. So the one-to-one property says now I can just look up into the exponent and set the exponents equal to each other and just ignore what the base is. So if x plus 7 has to equal 2x now I can just solve that linear equation for x. So why don't you go ahead and solve, get the x's on one side and solve for x? So you just subtract x, right? And x is going to be 7. So 7 is equal to x. So that might have taken us a while by guess and check. So I guess 2 to the 14th power is the same as 4 to the 7th power. Maybe you're good at guess and checking, or maybe you know what powers do. But so 2 to the 14th and 4 to the 7th are both equal to 16,384. So to me, I need that algebraic step. I can't just guess and check and just figure it out. Maybe you realize that this would have to be twice as much or something because it's 4 instead of 2. But number 3 is pretty easy, right? The bases are both just e, so you can just set negative x equal to 3 and solve that equation. So what would make negative x equal to 3? Divide by negative 1 on both sides. X would have to be negative 3 itself. So on number 4, what I would use is I would use the power family of 2. So I want to make both of these into a 2 so that I have the same base on both sides. So if I make this into a 2, what power does 2 have to get raised to get to 1/2? 2 to what power is 1/2? So if you flip it over, what power is that? Negative 1. So isn't 2 to the negative first equivalent to 1/2, I'm not changing the value, I'm just changing forms, I still have the power of x sitting there. So I haven't changed the value. 2 to the negative first is 1/2, and I'm still raising it to the x power. How do I represent 4? Well, I just did it up here, right? 2 squared. So on this side, I have 2 squared, and it's being raised to the x plus 4 power. So now my bases are the same. So I'm going to distribute my exponents with multiplication. So on the left-hand side, I have 2 to the negative x power equals 2 to the 2x plus 8 power. See how I use the distributive property there? So all I did was I changed into 2's so that I could get the base the same, so that now I can ignore the bases, right? Now I can just look up in the exponents and set the exponents equal to each other. And we hadn't really done that before, where we purposefully changed the base. Before, we were just looking at solving them with our eyes, thinking of what power it would be. So you're going to solve the equation negative x equals 2x plus 8. Collect your terms on one side. The answer might come out as a fraction. That's okay. So x ends up coming out as negative 8/3, right? Because I subtract 2x, I get negative 3x on this side. Divide both sides by negative 3. So I get x is negative 8/3. I don't think I could have gotten that one, by guess and check or thinking of the table of powers. So you really did need the table of powers to get to the same base, and then just linear algebra to get to what x is equal to. So I did all of those questions without using a calculator. So sometimes you can solve exponential equations without using a calculator because they're from the same power family. When you take a look down here at number 1 for in a minute, 2 to the x and 10 are not from the same power family, right? This would need to be like a 4 or an 8 or a 16. So we need a new strategy when we get down here, because we cannot force them to be the same base. Same thing down here. I've got an E and a 60. I can't force E or 60 to be the same power family. So we need a new strategy for down here. So the one-to-one property only gets us so far. So that's why if you know that they're from the same power family, you know which method to use. That's why we did the table of powers. So there's also a one-to-one property for logs. And when you've got a base of 3 on both sides, the stuff inside the logs has to be equal to each other, just like it was up here in the exponent. So in number 5, x just has to be 7. And in number 6, if you add the natural log of 3 to the other side, I think you can see that if the natural log of x equals the natural log of 3, those both have a base of e. They're the same function, so x has to be 3 in this problem. So if the bases are the same and there's just one log, you just set what's inside equal to each other. When you take a look at the back page, oh, I guess it's not 2 logs on the back page. On the back page, we've got 1 log, but it's not set up the same way. All right, so here's what happens when you can't change it to the power family that you want. 2 to the x equals 10. I know about what x is. X has to be somewhere between 3 and 4, right? Because 2 cubed is 8, and 2 to the 4th is 16. So my answer is going to be 3 point something. So how do I find out, instead of just guessing and checking? Oh, is it 3.1? Is it 3.2? 3.3? So there's got to be a way that we could get it more exact than that. So there's 2 ways that you can think of doing this problem. The first is by taking the log of both sides. So if you took the log of both sides of this problem, I'm going to show you the 2 different ways, and then you can decide which strategy you like best. If I take the log of 2 to the x, and I take the log of 10, taking a log is like taking a square root, dividing by 3. We're doing the same thing to both sides of the equation. If I continue to solve this, my next step is this power rule, right? I have an x up here in the power. Remember from yesterday, I can bring the x down front and write it as a coefficient. So this is really x times the log of 2 equals the log of 10. The log of 2 is just a number. I can evaluate that on my calculator. So my last step is I'm going to divide both sides of the equation by the log of 2. So x is going to equal whatever the log of 10 divided by the log of 2 is on my calculator. So I have to use a calculator. The log of 10 divided by the log of 2 is 3.32. Remember I said it was going to be between 3 and 4? So it's about 3.32 rounded. So what did I mean at the beginning that I could just change it into log form? So remember, if you have like 2 cubed, you don't have to write this down, but 2 cubed equals 8 is the same as log base 2 of 8 equaling 3, right? That's going between exponential and log form, but it means the same thing, right? 2 is the base, 3 is the exponent, and 8 is kind of what it equals. If I'm at 2 to the x equals 10, what I could do is just rewrite it in log form in one step to evaluate it. See how I would get the log base 2 of 10 equals x? Didn't I just evaluate the log base 2 of 10? Change of base formula, right? Log of 10 divided by the log of 2. So instead of taking the log of both sides, you could on your calculator do math log base log base 2 of 10, you're going to get that same number, 3.32. So taking the log of both sides and using the power is the same as just changing into log form. Gives you the same answer. I just was taught kind of old school where you take the log of both sides, but a lot of my students, because they've got the button right on their calculator, they like just changing it into log form. So I'm going to keep taking the log of both sides because that's, to me, mathematically what you would do. And I feel like changing into log form, sometimes you forget that. It's just a memorized fact. But in algebra, if you know what to do to both sides, you have a better chance of maybe remembering it. So I'm going to do the log 2 to the x plus 1 equals the log of 3. You end up bringing this x plus 1 down in front. That's the power rule. So x plus 1 times the log of 2 equals the log of 3. Divide both sides by the log of 2 because that's just a number. So divided by the log of 2. And then see how that's equal to x plus 1? Right? At the end, I'm going to have to subtract 1 from whatever I get. So on my calculator, I would do the log of 3 divided by the log of 2. Hit enter, and then just subtract 1 at the end. So 0.58. Are you kind of with me on what we're doing? Either change the log form or take the log of both sides. All right, so number 3. E to the x plus 5 equals 60. So your first step needs to be getting your exponent by itself. So your first step would be subtracting 5 to the other side. So e to the x actually equals 55. So e to what power will give me 55? Somewhere probably around 5, right? Because if this was the number 2, 2 to the 5th is 32, 2 to the 6th is 64. This is 2.7. So I don't know, maybe somewhere around 5. But instead of guessing and checking, you can either change it to log form or take the log of both sides. So here's a shortcut for you. Instead of taking the common log of both sides, there's a shortcut when there's a base of e, and it's taking the natural log of both sides. And when we start solving application problems, the reason this is a helpful shortcut is because what base does the natural log have? e. So isn't this like taking the natural log or the log base e of e, right, to the x power? Isn't that just 1 right there? So when you bring your x down front, I'm running out of room. It's really x times 1 equals the natural log of 55. So this whole thing right here is equal to 1. Because remember our property yesterday? Where is it? When you have the base the same as inside the log, it's always equal to 1. So if the base is e and the inside number is e, it's equal to 1. So the natural log of e is 1. Just like the log base 10 of 10 is 1, or the log base 8 of 8 is 1. So a shortcut when we start solving application problems is take the natural log of both sides. Then there's only one button I have to press on my calculator. I'm just going to evaluate the natural log of 55 on my calculator because that's another button. Right? So natural log of 55, 4.01. I guess I was a little off with my estimate of 5, but 4.01. All right, I'm going to do 4, and then you're going to try 5 and 6. So number 4, I've got to start by getting e by itself.